we've introduced the idea then, with the collision theory, that in order for molecules or ions or whatever to react, it's not enough for them simply to collide. They have to hit each other hard enough with sufficient energy that you can break some existing bonds in order to then allow new ones to form. So gentle collisions won't work. The molecules will simply bounce off one another without anything happening. Now, what makes this very complicated, and this is the really important idea in all of this, is that all of the molecules in a gas or in a solution or whatever don't move at the same speed. And you can see why that would be if you just picture molecules in a gas moving around and colliding with each other. Because, depending on what angle they hit each other at, relative to their directions they're travelling in, and, their relative velocities in a particular direction, sometimes particles will slow down, sometimes particles will speed up, and they're going to end up with a whole range of different velocities. So you can't just make a simple statement like saying, at this temperature particles will be travelling fast enough that they'll have enough energy to react, and at this temperature they won't. Because it's not like that, because the particles don't all move at the same speed. That's a really important idea. So Ludwig Boltzmann was the person who realised that you could deal with that problem by applying statistics. Because he realised that, yes, particles don't always move at the same speed, but that the distribution of speeds the particles will be moving at will always be the same at a given temperature. And because the number of molecules in a system is so huge, the statistics work sort of perfectly. And so the distribution is entirely reproducible every time you go to a particular temperature. So it's very important thing when it comes to explaining everything to do with rates of reaction. So let's have a look at the Boltzmann distribution, and this diagram that we're going to draw now is something that you have to be able to draw. So you have to be able to label the axes correctly and draw the shape of the curve. So what we're going to draw is an axis system like this. This axis is usually labelled number of molecules. If you know about statistics, what this really is probability density up here. But just to simplify things, you can think of it as the number of molecules. And this is simply energy along the bottom. Kinetic energy, basically. It's related to how fast the molecules are moving. So what this curve is going to show you is, in effect, what's the probability of molecules having a very low energy, or a middling amount of energy, or a high amount of energy. So both of these start at 0, so you need to label your zeros on there. And then the curve has this kind of shape. So it rises up to a peak, and then it comes down more gradually. And it moves asymptotically towards this axis. What that means is that it sort of converges with it, but doesn't cross it. And the best thing to do is just to sort of stop drawing it there before it gets too close, and then you avoid the issue. What you absolutely mustn't do is have this curve crossing the axis, because obviously you can't have a negative number of molecules, and nor should it slam down into it, because as I say, it's just going to come closer and closer to it and sort of merge, but not cross it. So the key features when you draw the curve up: label the axes correctly, make sure it starts at the origin. So in other words, there is zero chance of a molecule having no energy. And again, you can just sort of picture that. If there are molecules whizzing about in all directions, the chance of having one sitting absolutely stock still is negligibly small. So it starts at 0, it rises up to a peak. So what that's saying is that this middling amount of energy, that's what the majority of molecules have. That's what the highest number of molecules have, is an energy in this kind of region. but then there's a significant minority with a much bigger energy, tailing all the way up to here. So this matters because, as we've said, there's this idea of an activation energy. So remember the diagram, that if we have an enthalpy profile diagram, so if these are reactants and this is the product, that's delta H of reaction, but that doesn't control the rate. What controls the rate is the activation energy, the fact that you have to have a collision energetic enough to reach this high energy state. And that energy gap is the activation energy. And unless molecules have sufficient energy when they collide to reach the top of that hill, they can't cross over to the other side and move down to the products. So that activation energy is a specific amount of energy, and therefore we can mark it on this diagram. Now, depending on the reaction, it could come anywhere along this axis, but for many reactions it's actually well over towards this side, so it's somewhere on the tail. So we can mark the activation energy like that on here. And that's a very important thing. So what we're saying is that molecules with energy in this range, they have enough energy to react when they collide, but these ones don't. Now we can quantify what proportion of molecules come in this group. In other words, what proportion of the total population of molecules have sufficient energy to collide. Because the area underneath this graph, if you do maths, you think of it as the integral of this probability density function. The area underneath the graph represents the total population of molecules. And so the area above this line, which we can shade in like that to highlight it, that area relative to the total area represents the proportion of molecules with enough energy to react when they collide. So you can sort of label your graph like that and explain that that means the population of molecules with enough energy to react when they collide. And that's why this distribution is so useful, because you can calculate that. The Boltzmann distribution is not an experimental result, at least you can verify it experimentally, but that's not what Boltzmann did. Boltzmann figured it out by thinking about statistics and came up with a mathematical equation. And so you can use that equation to predict absolutely accurately what the proportion of molecules will be with enough energy to react at a given temperature, so long as you know what the value of the activation energy is. So what we can then do with this diagram is to say, right, well, how does this relate to the effect of temperature? Because we know that temperature increases the rate of reaction. But the question is why? Now, in fact, there are two aspects to that, and we need to make sure that you understand both of them. If we increase the temperature, it means there's more energy in the system. So on average, a molecule is likely to have more kinetic energy and therefore be travelling faster than it would be at a lower temperature. And so that's going to be reflected in the Boltzmann distribution. So what happens is that if we move to a higher temperature, the position of this peak, the most likely energy, is shifted towards higher energy. So we get a different curve at higher temperature. And what it's going to look like is something like this. Okay, so you can see that I've drawn it with the peak clearly shifted to a higher energy value. That's characteristic of higher temperature. So we can label that there to make that clear. But the other thing that you'll notice is that the height of the peak has dropped down, and again that needs to be very clear when you draw it. Now the reason for that is clear when you remember that the total area underneath the curve represents the total population of molecules. If we change the temperature, we don't change the number of molecules, and so the area under the curve underneath this pink curve has to be the same as the area under the black one, because it's the same number of molecules that we're talking about. So if we spread it out more in that direction, it has to be squashed in that direction in order for that area to stay the same. So when you draw these things, that needs to be really clear, that the peak is shifted this way and that it's squashed. Now what does that tell you? Well, the first thing is that it tells you that on average the molecules are travelling faster. And clearly if they're travelling faster, they're going to hit each other more often. You know, if molecules are moving along very slowly, there's likely to be a long time interval between, you know, when they happen to come together and collide. Whereas if they're whizzing around all over the place, they're going to have much more frequent collisions. So that's the first factor. Okay, so molecules move faster on average. And it's very important to put those words on average in there, because you know some of them are still moving incredibly slowly, so you can't say they're all moving faster, because some of them still have a kinetic energy close to zero. It's just that the average is shifted, so molecules move faster on average at higher temperature. Which means that they collide more often. Don't say more collisions, because obviously that depends on how long you wait. People lose marks by saying, you know, they move faster on average, so there are more collisions. But what you mean is there's more collisions in a given time. And you can say that, or it's easier just to say collide more often. And that will give you a higher rate of reaction. And that's quite important. It turns out that for reactions that have a very low activation energy, that is the limiting factor. But that's only a tiny minority of reactions. Actually, for most reactions, that's not the most important point. So yes, you should mention it, but what's much, much more important is the activation energy thing. So we can understand that by marking the activation energy on here. Okay, so remember the activation energy is just a particular amount of energy which we can mark on like that. Okay, so there's EA, that's the shorthand for the activation energy, and that's independent of temperature. It is what it is, it's a fixed amount of energy, and what we're saying is that's the proportion of molecules with enough energy to react at the lower temperature. But you can see that the result of shifting that curve to the right is that at the higher temperature you've got a much bigger proportion of molecules with enough energy to react when they collide. And if your activation energy is in that part of the curve, that has a much bigger effect on the rate than this does. So you need to be able to do this diagram, and just doing the shading of the areas like that makes it very clear. But you need to be able to put it into words as well. So a higher proportion of molecules have energy greater than the activation energy. If the temperature is higher. And that means that when collisions occur, they're much more likely to be successful. Okay, because if there's a higher probability that they'll hit each other with total energy exceeding the activation energy, that equates to a higher probability of successful collisions and therefore an increased rate of reaction. And as I say, that for most reactions is actually a bigger effect than this one. So a higher proportion of molecules have energy greater than the activation energy if the temperature is higher. So that means that the probability of a successful collision, and you can use that phrase, people reading it will understand what you mean by that, a collision that leads to reaction. So the probability of a successful collision is increased, and so you get a higher rate of reaction. And as I say, this is typically, usually, the biggest effect. So when you're writing about temperature dependence, you should mention this, but most of the marks will go for this, because this is the biggest effect. So practice the diagram, use the shading to indicate this big difference in population of molecules with enough energy to react, but make sure you can put it in words as well. And the consequence of that is this well-known effect that reaction rate increases with temperature.